Welcome to this final lesson in the view optimization course using Galapagos. And in this lesson we're going to run our Galapagos solver to see the results. And after that we're going to look at some more ways to fine-tune the result if needed, using exponential functions as a base. So let's get to it. And before we run the simulation, I want to visualize our views a little bit better using the gradient component. So we color our lines based on how good or how bad they are. So let's insert a gradient component. And let's lock it so we don't accidentally move the handles. Nice. So those are the view rays. The only thing is, those are not the view rays I want to visualize because some of them are extremely long, and that's because we saw in the previous lesson, we rewarded views that look at a certain landmark. I want to relink this component to the original view rays before we extended them, and that's this one, the output of this one. Nice. So what do we need? We need to get the length of the view rays. So let's get them using the length component. And that's going to be the input for our small t. Now we need to get the bounds, the L0 and L1, and we can get a bounds component for that to retrieve the bounds from our view rays. Don't forget to flatten the n input. So our view rays are between 0.3 and 810. And if we insert the deconstruct domain component, we can get the individual numbers. Just like that. So now with a preview geometry custom preview, we can preview our lines. So this one goes in the G, the geometry to preview, and the S, those are the shaders or the output of our gradient component. And you can change the preset however you want. I mean, in our case, I think it's fine. So red indicates bad views and blue indicates, or cyan indicates that it's good views. So I think that more or less represents it. That's fine. Great. So let's run our solver. And before we run it, don't forget to first hit the reset button. So we reset our range from our view quality fitness value. And also don't forget to hit randomize on all the sliders just in case. Just right click on a gene pool component and hit randomize. This so Galapagos starts with a clean slate. Now let's check our sliders, the sliders we set. So I think we're going to penalize views that are below 40. I think that's fine. I think I increased. No, it's still 15. I think the minimum distance is 15. We can also switch it to 20. So there's a little bit more distance between the buildings. I think that's fine. What else? Yeah, I think 5 is also fine as a prefer view factor, the weighing factor. The only thing is the location of our preferred view. I moved a little bit towards here, so I think that's also fine, depends on where you want to locate it. You can use these two sliders to locate your preferred view. I think that's also fine. Let's keep it like this. So what else? I think we're there. Great. So let's go to our Galapagos component, double click it. So the options, so fitness we're going to optimize for 0, that's also fine. The initial boost is 10. I increased it a little bit. So we have a wider net to start off with for our population, our multiplication factor. The inbreeding I set it to -75, so we have a lot of zoophilic relationships as offspring. So that's also fine. Let's go to solvers. Select your fast option located here. And let's hit Start Solver to start our solving process. So you can minimize Rhino to make the process go a little faster. So like I mentioned in the previous lesson where we first ran Galapagos, it's going to take some time. Usually it takes between half an hour and 45 minutes, or half an hour and an hour, depending on how long you want to run it. And also to see how the fitness value shrinks. So I'll see you in half an hour. So this is more or less like 40-45 minutes of runtime. And you see that the difference between all the genomes is pretty small. There's not a lot of improvement anymore. They hover around 0.43. So it's time to stop our simulation, and we can do that by hitting the Stop Solver button. So let's select our best genome and hit Reinstate. And let's go back to Grasshopper. So let's examine the results. So let's go to our 3 fitness values. Let's start with the shortest distance. As you can see, they're almost above 20. 19.17 is the lowest one. We specified 20 as the minimum, so it's almost. Let's check the footprint areas. So the top 2, they're fine. The bottom 2 are a little bit too low. They're 934 and 950 was, let's say, the minimum they could have. So they're a little bit too low. The good thing is that the view quality, those are pretty good. If you look at the Rhino viewport, the top view, you see that most of the buildings are orientated towards the view I wanted them to be. And they rotated nicely towards that, so that's pretty cool. Now, I wanted to show you another way how to maybe even improve the fitness values even better. Because now we only took a look at linear functions, except the one from the view factors, the penalization, where we squared our result. And that's more or less what we're going to do also. Instead of using a linear function, we're going to use an exponential function. So let's go to our website we used previously to draw a graph, so I can explain it a little bit better to you. So let me first draw just the linear function x, which represents our fitness function how it is now. So 0, 0 is the best outcome and 1, 1 is the worst one. And it's exactly linear. When a genome is 0.5, the result is also 0.5. But let's say we want to exponentially penalize the outcome. We can use an exponential function. So let's start with the most basic one, which is x squared. A function you are well familiar with, I'm sure. Now, the problem with that is that between 0 and 1, this function is actually smaller. The outcome is smaller than the x. I mean, if I use 0.5, for instance, the result is 0.25. And that's not what we want. I mean, if the value is above 1, then you start seeing that the outcome is higher. We need to move this graph 1 to the left and 1 down. So the outcome will always be above 0, will be more than our linear x function. Now the way to do that is to add 1 to the x. And then we subtract 1 to move it 1 down. And now as you can see, we have an exponential function. If my genome is 1, the result is 3, so it gets punished more. But of course, if it's 0, it's still 0. But as soon as the genome increases all the way to 1, you see that it gets penalized exponentially. And we can even make it more extreme. Let's say you want, instead of squaring it, we want to do it to the power of 3. We can do x plus 1 again. And then instead of to the power of 2, we're going to do it to the power of 3. This one is even more extreme. Let me also reorder our graph settings a little bit. Or -1 to 40. -1 to 1. a little bit smaller. So let's say 20. Just like that. So here you see the exponential result. So our linear function is just, when it hits 1, the worst outcome, let's say, is just 1. But if you square it, it's 3. And if we do it into the power of 3, you get 7, and so forth and so forth. Now, if you're going to use this logic, going back to our Rhino again in Grasshopper, if you want to be really strict and say like, well, I really don't allow footprints that are outside of my 5% tolerance, you can use this exponential function to penalize it even more. So we need to use a small expression. And we're going to use that formula to do it. So it would be x plus 1 to the power of y, because we're going to use an input for that to specify the number, the exponent. And the y is the weighing factor. So let's use 2 for now. I think that's more than enough. But you can increase it depending on how the result turns out. I'll move everything a little bit to the right to get a little bit more space. The outcome of this is between 0 and 1. And by using this function, I'm basically exponentially penalizing it between 0 and 1 again. So this one goes in the B instead of the other one. And we can do the same for the shortest distance. And that one goes in the C. Let me also specify a separate weighing factor. Nice. Now the only thing remaining is also a weighing factor for our views. So let's insert that also, so we play it fair. Let's call it W for weighing factor. And we can simply just multiply it by W, like that's it. Let's set this one to 1. So these values, you can play around with them. What your importance is towards the separate fitness values, weighing them. If you say like, well, I don't really mind that my area footprint is a little bit off, and also the shortest distance, I don't really mind. But what I do mind is the views. I really care for that. You can increase this value, let's say set it to 3 or 2 or 4 even or 5, depending on how you value the fitness values. Before we end this lesson, I want to show you another optimization plugin for Grasshopper that uses a different method than the Galapagos solver. And it's located here. It's called Silvereye, and it's a really nice tool. I've tried it a couple of times. Like I said, it uses a different method to optimize. It's a little bit the same as Galapagos. It also uses a lot of different particles to start with. But the way it optimizes is a little different. It works a little more straightforward than Galapagos, and the results can be obtained more fast. You reach an optimum way more fast than Galapagos. For instance, the solution I got with Galapagos took me around 45 minutes to an hour. If I use this particle swarm optimization plugin, the Silvereye, I get the same results within 10 to 15 minutes, and really nice, really well done. I even get better local optimums than Galapagos. So it's definitely worth to check it out. And the nice thing is that it has the same inputs as Galapagos. You just input your parameters or your sliders, and you specify a fitness value. And the options are very straightforward. I think you just need to specify either the amount of iterations or the runtime, and you run it, and that's it. So it's very easy, very fast. So definitely worth to check it out. Now on a final note, I want to advise you not to use these final shapes as your final building masses. Of course, they should be treated as a rough start of your design. So this is the point where you do some prints, put some sketching paper on top and start designing your building. But the nice thing is at least you have a rough base guide to start with. and that you know that these raw outlines, they represent 4 buildings that are really optimized for views while maintaining a certain distance and a certain amount of square meters. Thank you so much for watching this lesson and also watching this course. I hope you find it informal and I hope it may help you on your way. Thanks for watching.